we're going to review it, and I can put the key up there. I can talk about some problems. Some of them I might need to do with you guys. But I'm going to have you fill out a reflection form about the test as well too. So just to gather some data. All right, today we're going to talk about exponential functions. So we've been talking about properties of exponents in 2.1 and in 2.2, but now we are going to take those properties and turn them into functions with inputs, outputs, domains, range, that type of stuff. We'll look at the graph of some exponential functions as well, which I'm sure you guys talked about previously in Algebra 1 and or Algebra 2, okay? All right, just some basic properties of an exponential function, but it's just a function in the form of f of x equals a times b to the x. The important thing to note there is that b, your base, is what is being raised to the exponent of x, okay? So your variable is now up in the exponent. Normally, we will have numbers that we plug in for a and b. You can kind of think of that a as the same a that's in front of a quadratic, like ax squared plus bx plus c. It's kind of like your leading coefficient. And we consider these functions where a is positive and b is positive as well too, and b is not equal to 1. If your base was 1, it would not be an exciting function because 1 raised to any power is equal to what? It's just equal to 1, right? So it wouldn't be very exciting, okay? So our base is not going to be equal to 1, okay? All right, now, if I open Desmos with this model, let's see how these variables affect things, okay? I told you a, you can just think about like the a that's in front of ax squared plus bx plus c. So in a quadratic, what your a value changes is a vertical shrink or a stretch. So what it really does is it changes how your parabola, like if it's ax squared, opens or closes like how wide it is, okay? And it performs very similarly in an exponential model as well too. So if I press the play button, you see that a is running between 0 and 5. So then, what we would expect to have happen where it just kind of changes the shape a little bit does indeed happen. It can stretch it, also shrinks it, flattens it out a little more as it gets in between 0 and 1. But let's see how our base changes things here. Oh, hold on. Wait till my a value gets back to where I want it to be. And shoot, I'll just do this. Okay, whatever, 1.2. All right, and then if I affect my base, let's see what happens. So obviously, like you can see very quickly, it's a much more dramatic and sharp increase as my base increases. But then notice what happens when I get close to 0. Whoa, it flips. Why does it do that? And what type of values does that happen at? So if we look at it again, yeah, in between like 0 and 1 is when that happens, okay? That's because, does anybody know what kind of model you get when your base goes between 0 and 1? What that's referred to as? There were two types of exponential functions that we studied. One of them looks like this, and the other one looks like that. Like that. Michael? Decay. Yeah, so this would be exponential decay, whereas when our base is greater than 1, strictly greater than 1, we would say it is exponential growth. Okay? Have we heard that before? Exponential growth, exponential decay? All right, super. Cool. All right. So just some other properties of exponential functions. Your domain is all real numbers. So picture that graph in your head while we talk about these things. You can plug any number in for x. Your range is all of your positive real numbers. Now, of course, if I shift it or I reflect it, that changes my domain and range. But as far as my parent function goes, your range is just your positive numbers. So anything north of 0. There's no x-intercepts. That's because the x-axis is a horizontal asymptote, but your y-intercept is 1. Now that can change depending upon if you have a leading coefficient. So this is just when we have f of x equals b to the x, okay? All right, and then if b is in between, or if b is greater than 1, our function is increasing, it's 1 to 1. That is called exponential growth. And then like Michael pointed out, if b is in between 0 and 1, then it is exponential decay. Your graph is decreasing, but still 1 to 1. All right, enough of the boring stuff. Let's get into the fun stuff. All right, so let's consider f to be an exponential function, and then they gave us a bunch of values. It says f of 0 is 3 and f of 2 is 12. We would want to find what is f of negative 2. Okay? So best place to start is to look back and say, okay, well, f of x equals a times b to the x. Let's go ahead and write that model down. F of x equals a times b to the xth power. Okay, so using those values that they give me as reference, I want to try to figure out what my function is. Okay, starting with 0 is a great place to start. Okay, so if I plug 0 in for x, it tells me that my output is 3. So let's plug in what we can. We would have a times b to the 0th power. But what is b to the 0th power?
1.
So that gives me which variable then? Yeah. So anytime that you plug in 0, if your graph is not shifted up and down and left and right, oh my God, Ethan, get it together. Then when you plug in 0, that output is going to tell you what your y-intercept is, which is also what our starting place is if you consider it to be like the practical application problem, okay? Well, now that I know that a is 3, I can use that to help me find b coupled with my other value that they gave me. So they also told me that f of 2 is equal to 12. Well, let's try to see if we can figure out what our base is then, okay? So plugging into this model again, f of 2 equals 12, so 12 goes in for f of x. My a value is 3, and then, thank you, Avery. And then we're going to multiply it by b to some value. Hey.
You said your attendance.
I'll do it.
Thank you.
No, thank you. So then b to what power? Well, they said f of 2 equals 12. So the power we're going to raise it to is the second, okay? I was doing so good for so long. What time is it? 20 minutes left in the period. Yeah, I should have done it by now. All right, what do you guys want to do next? The goal is to find b, so we should do what? Yeah, I agree. All right, so we divide both sides by 3. Get 4 equals b squared, leading us to do what next? Yep. So we get b is equal to plus or minus the square root of 4, which is going to give me 2. However, on the last slide, what did they say about our base? Our base needs to be what? Our base had to be greater than 0, positive, right? So because of that, my b value can only be positive 2. Okay? So then if I write my function, f of x, I got that it was 3 times 2. Oops. Two to the x. I can put 2 in parentheses to indicate that it's multiplication. So 3 times 2 to the x. I like the way that's written. But then to answer the question, it says we need to find f of negative 2. All right, so now I'm going to plug negative 2 into my value for x. So f of negative 2 equals 3 times 2 to the negative second power. All right, I got to deal with 2 to the negative second. What is that? 1 over 2 to the second or 1 over 4, right? So I'd end up with a final answer of f to the, well, let me do this. 2 to the negative second. So then I end up with 3/4. Cool with that? Super. Okay. Now, that value in my mind makes sense because if we think about what the graph of that would look like, I mean, it's going to be, I know that when I plugged in 0, I had a value of 3, right? So it's going to be something like that. Just a general shape of the graph. So if I plug in something like negative 2, I would expect it to be a value that's pretty close to the x-axis, so 3/4 makes sense in my mind. Okay. All right, cool. Let's keep going. Now, a couple of formulas, one of them that you are already well familiar with. We had been working with a of t equals a sub 0 times 1 plus r to the t. You guys saw it like this, though. A of t, or actually, you didn't even do it as a function. You saw it like this. A equals, what letter did we use, though? Yeah, so a equals p times 1 plus r to the t. Okay, so we saw it like that previously. But we do need to get used to multiple notations, especially if we're working with functions, we're doing, with respect to a variable. Now, the a sub 0 means your amount at time 0. So you'll see that like subnote and a value that's, kind of like lower next to the a different value there. Get used to that notation. We'll be working with that as well too, okay? Now, our p-value or our a sub 0's value is our initial amount, and then your r value is your rate. So it's either your growth or your decay rate. We could be talking like annually, we could be talking monthly, daily, just depends upon the context of our problem, okay? It's growth if your r value is greater than 0. If your r value is in between -1 and 0, we would say it is decay, all right? And then our value t is time in months, years, months, or days, okay? It just depends on the context of the problem again. However, this value, or this formula to the right, is a little new. We haven't worked with this one yet. You guys may have seen it in the past. But we use this value in some settings for very specific things. So your a sub 0 value is still your p-value. That's your initial amount. A of t is whatever your future amount will be. But they tell you that k is the time needed to multiply a sub 0 by b. Now, that's like a weird thing to think about how that's worded. But you'll see some problems in your homework, practical application problems, where they might say you're investing your money and you want to know how long it'll take to equal 3 times the amount. Or you want to, let's say you have something that's like going away or decreasing. We want to know how long it'll take to equal half the amount. This model is the best model to use in those situations. If you're trying to figure out how long it takes for your value to either double or triple or some sort of value that's multiplied. And then your t-value is still in years, months, or days. A common place that this is used would be like radioactive decay. So like radioactive half-life of an element, something you guys have probably talked about in science class. That's one of the, this is the most common model for that, okay? All right, a bank says that if you open a savings account, you can double your money in 12 years. That's pretty good. Express A of t, the amount of money after t years, in each of the 2 forms listed below. Okay, we're going to work with the first form first because we're used to that one. We're familiar with that one. So let's work with this form first, okay? They don't really give us a lot in the problem. It just says if you open a savings account, you can double your money in 12 years. That's it. They didn't tell you how much you're starting with or anything like that. We just wanted to come up with an expression for this situation using these models, okay? So because of that, I'll start plugging things in. I don't know what my starting amount is. They don't tell me. So I'm going to keep it as a sub 0. Okay. Now, 1 plus r. They don't tell you the rate at which it's happening either, right? So we have to keep r general in this case. But what about t? What's that going to be? Yeah, they tell us 12 years, so there's some information I can plug in. What about on the left side? Double a sub 0, right? So I would literally write 2 times a sub 0 because that is what our ending amount is going to be, is we doubled it, okay? All right. Well, let's go ahead and solve for r because let's see if we can come up with an expression for that. What can I do to both sides? So divide both sides by a sub 0. So then that gives me 2 equals 1 plus r to the 12th power. I want to solve for r. What should I do to both sides? 12th root, that's pretty aggressive. The 12th root is pretty intense, but that is exactly what we're going to do. So 12th root of 2 equals 1 plus r. There's only one thing left to do, which is what? Subtract, right? So I'm going to subtract 1 from both sides. So then my value for r is going to be the 12th root of 2, and then outside of that root is minus 1. Hey, solve for my rate. That's pretty good, my interest rate. But my goal is to express a of t. All right, so if I do that, let's do it right here. A of t equals, well, I would have, I'm actually going to write it underneath those. Okay, I'm going to do it over here. All right, so the a of t equals, again, a sub 0 times 1 plus, well, I know what r is now. It is the 12th root of 2 minus 1, and then to the t. But if I simplify that, inside that parentheses, what simplifies? My 1's cancel out inside the parentheses, right? So I would get the 12th root of 2 and then to the power of t. Now, there's not really much more that I can do with that, so I'm going to leave it like that for now. Let's work with my other form, though, okay? So it says a of t equals a sub 0 times b to the t over k. So we need to remind ourselves a little bit about what those values are. Well, a of t is what my future value is going to be. We kind of already played that game. That's 2 times a sub 0. So I'm going to write that again on the left side. Equals a sub 0. I don't know what I'm investing. Okay, and then my base, let's look back at my formula. So it says that k is the time needed to multiply a sub 0 by b, okay? We were doubling our amount, right? So then my b value in this case is going to be what? 2, because I want to know how long it's going to take to double it. So 2 is the value that goes in for my base in this case. And then t over, and then k was how long it took before it doubled. And how long did they say it would take? 12 years, okay? All right. Now, if we look, oh, sorry. I should leave my other, I should leave this as a of t, not 2 times a sub 0. Sorry, my left side should be a of t. A of t. All right, now, if we look, that looks pretty similar to that form that's already there, right? Yeah, the only difference is a of t equals a sub 0. They took the t over 12, and can I move that, like the 12th root inside that parentheses? I can. I can leave it as, I could write it as 2 to the 1/12th power if we wanted to, and then leave the t out there. Those things are equivalent to each other using those properties that you guys learned the past couple days. And then these forms are equivalent. I could write it as the 12th root if I really wanted to, but other than that, we see that these two are equivalent. So are these equivalent? Resounding yes. Now, which one required more work? The one we already know, right? If we're fitting it into this model, it's so much faster to do the value that's on the right. So, all right, speaking of half-life, a radioactive isotope has a half-life of 5 days, meaning that it takes 5 days for half of the substance to decay. At what rate does the substance decay each day? All right, now this is radioactive decay. So because of that, my graph looks something like this. Okay, so it decays by half after 5 days, but then it's a slow burn to that horizontal asymptote there afterwards. Okay, all right. Let's work with both formulas and show that they are equivalent in this case. All right, so radioactive, so we have half-life of 5 days. At what rate does the substance decay? So if we use our first model that we learned, a of t equals a sub 0, 1 plus r to the t. Okay, I don't know what a of t is. I don't know what a sub 0 is, but I can come up with an expression for a of t. I don't know what my starting amount is, so I'm going to leave that as a sub 0. 1 plus r. And then what's my time step in this case? 5 days. What would my a of t value be? half what? Half of the original, right? So 1/2 of a sub 0 is what I would plug in for a of t. So if I start this problem the same way, I divide both sides by a sub 0. So 1/2 equals 1 plus r to the 5th power. Now what do I want to do? 5th root, okay. So then 5th root of a half, looks weird to write it that way, equals 1 plus r. And then I don't need those parentheses anymore. I can very easily solve for r, and I would get that my r value is equal to the 5th root of, can I write 0.5? You guys cool with that instead of 1/2? Minus 1. I'll write it like that. I could leave the 1/2 in there. It doesn't really matter. So then when I write my final answer, I would get a of t equals a sub 0 times 1 plus the value I just found for r, the 5th root of 0.5, and then minus 1 to the power of t. Which, simplifying that, gives me a sub 0 times 5th root of 0.5 to the t. Now let's see how that compares to if I use my other formula. A of t equals a sub 0 times b to the t over k. Can I do this? This is a thing that I can do. Tap that and then change the color of it. Does it do that? Oh my God! That's pretty cool. I didn't know it did that. We all learned something today. I learned something. You guys apparently knew that that was the thing. Okay. Let's plug in my values. Okay. All right. In this case, what is my b value going to be? What do I want to have happen? I want half, right? So a of t equals, I don't know what a sub 0 is, but we would want 1/2 to the power of what? T over 5? And if I look, I mean, isn't that like, hold on, let me lasso this guy and bring it over here. Oh shoot, it didn't work. Try again. Ah, yeah. Okay. I mean, aren't these like pretty much equivalent? Because if you look, I have the 5th root of 0.5, but 0.5 is my base here. And if I really wanted to, I can break that t over 5 root apart and make it 0.5 to the 1/5 and then raise to the t. So they are equivalent. Okay. All right, questions there? Okay. Is it 45 or 40 that it rings?
45.
It's 40. Dang it. Okay. All right, where your homework is 3 through 17 odd, and then 19 through 21 on section 2.3. Tomorrow we're going to do an in-class review. We will complete and in-class review. Shoot, it should be an, not and. In-class review, and then aim for a quiz on Wednesday. So Wednesday we'll do a quiz, and then probably start 2.4, okay? I got to figure out what to do with you guys on Friday. Mr. Mosier's video is probably what we're going to do. I'll give you your test back tomorrow. That way we have time to go over them for a couple minutes, and then you guys can work on your review. All right, as always, good job putting problems on the board. You guys are superstars.